Hi everyone, I'm Neil Trevett and I work on developer ecosystems at NVIDIA and I am president of the Khronos group. I'm going to be giving you the latest updates on Khronos's open standards for accelerating interactive experiences within the ARM ecosystem. So let's start by introducing Khronos. If you haven't come across us before, Khronos is an open standards consortium. We provide a safe space for the industry to cooperate and create interoperability standards. These standards enable applications to access the power of 3D graphics, virtual and augmented reality, and parallel computation. We are a non-profit organization, and all the standards we create are open and royalty-free for the industry to use. We have been creating open standards for 20 years now. We have almost 160 members that includes everyone from the largest companies down to small startups. Any company who wishes to join Khronos is welcome to participate and to have a voice and a vote in how Khronos standards evolve. So here are the most active standards currently being developed by Khronos. There are four main groupings: 3D acceleration APIs, including Vulkan, OpenCL ES, and WebGL, initiatives around 3D asset formats, including GLTF and the new 3D Commerce Working Group, and the OpenXR API standard for portable and augmented and virtual reality. And lastly, a family of APIs and languages for parallel computation. But today, we are going to focus on these four highlighted standards: Vulkan, OpenXR, OpenCL, and SPIR-V. So let's first look at Vulkan, which is a new generation 3D API that provides explicit low-level access to GPU acceleration. And unlike the previous generation OpenGL and OpenGL ES, which used a large, complex driver to manage the GPU for the application, Vulkan enables an application to manage its own memory management and multi-threading exactly as it wishes, and then efficiently drives commands into the GPU via multiple graphics and command queues. Vulkan also removes the GLSL front-end compiler from the driver by ingesting Khronos' SPIR-V intermediate language, and also takes debugging into loadable layers. So Vulkan is a much thinner driver than the traditional OpenGL. Vulkan can enable significant increases in performance, particularly on CPU-limited systems, and provide more reliable cross-vendor application portability. Not only is Vulkan a new generation 3D API that provides low-level explicit control over GPU hardware, it is unique as it is the industry's only open standard new generation GPU API, and so it's not restricted to ship only on one vendor's platforms. In fact, Vulkan is now being shipped by every GPU vendor, is adopted by the leading gaming and application engines, and is available on almost every platform, including desktops, mobile, consoles, embedded systems, as well as cloud and streaming services. And where Vulkan goes, the latest rendering technologies, for example, such as ray tracing, can follow. The most recent version of Vulkan, which is Vulkan 1.2, launched in January 2020 and integrated a number of proven extensions, including timeline semaphores for streamlined synchronization and functionality for enabling apps to easily migrate between DX12 and use HLSL shaders. The key ongoing roadmap discussions post 1.2 are on the right hand of this slide and include ray tracing, as well as variable rate shading and hardware-accelerated video encode-decode. This new functionality will ship first as extensions, and those extensions that are accepted by the developer community are strong candidates for integration into future core specifications. In fact, Vulkan Ray Tracing has already shipped provisionally in March 2020 as a set of Vulkan, GLSL, and SPIR-V extensions that seamlessly integrate ray tracing into the existing Vulkan framework. This is a significant milestone as it is the industry's first open, cross-vendor, cross-platform standard for ray tracing acceleration, and can be deployed either using GPU compute or dedicated ray tracing cores. Vulkan ray tracing will be familiar to anyone who has used ray tracing using DX12, which is called DXR, But Vulkan has introduced some additional functionality, such as the ability to load balance ray tracing setup operations onto the host's CPU. And although ray tracing will be first deployed on desktop systems, ray tracing in Vulkan has been designed to enable and encourage ray tracing to also be deployed on mobile. So how do you use Vulkan ray tracing? Like many other ray tracing APIs, the first step is to build the scene geometry into an efficient two-level acceleration structure, so searching for ray intersections can be performance optimized. The precise internal organization of the Vulkan acceleration structure is opaque to the application, so that hardware vendors can optimize it to match their own architecture. And so Vulkan simply provides API calls to supply geometry to be built into the structure by the Vulkan driver. The second step is to launch rays into the scene to calculate how those rays intersect and interact with scene geometry, materials, and light sources, and to process those intersections with programmable flexibility to enable a wide variety of visual effects. Vulkan provides two ways to dispatch rays. The first method uses a new ray tracing pipeline that enables the application to compile a set of shaders into the pipeline to handle any desired ray and material processing, and then launch a grid of rays into the scene with the ray tracing pipeline invoking the appropriate shader when intersections occur, or a miss shader if no hits occur for that ray, which can be used to render the sky in an outdoor scene, for example. The second technique to fire rays, which Vulkan calls ray queries, is much more explicit and enables any type of Vulkan shader to launch a ray at any time and process the intersection data however it wishes. This is a very flexible technique, as the shader can also control how traversal proceeds through the scene. So that's a lightning tour of Vulkan. Next, let's talk about the OpenXR standard for portable, virtual, and augmented reality. OpenXR defines a common API that all XR runtimes can expose to application and engine developers. This enables XR software to be written once and run on any XR hardware that supports the OpenXR API. For the first time, XR applications don't have to be rewritten to run on each runtime in the industry. It's important to understand that OpenXR does not prevent device drivers to continuing to innovate in design and implementation of their hardware and runtimes, but the industry has just now agreed how to consistently expose the capabilities of the XR devices and runtimes to software developers to avoid industry fragmentation. OpenXR is supported by almost all the leading companies involved in building AR and VR systems throughout the industry. It's interesting that as well as providing portability, OpenXR has enabled the industry to come together to share learnings from the first generation of XR APIs and to collaborate to create a new generation XR API with cutting-edge capabilities and a flexible, extensible, future-proof architecture. So OpenXR is now being deployed by major device manufacturers around the world. The OpenXR 1.0 specification was publicly released in December of 2019, and since then Khronos has been working hard to release the OpenXR conformance tests to enable devices to be tested to be compliant to the OpenXR specification. Additionally, the first officially conformant devices are now shipping. This includes all Windows mixed reality headsets and the HoloLens 2 from Microsoft, plus the Oculus Rift and the Oculus Quest. Oculus has announced that developers can now submit their OpenXR apps to the Oculus Store. Pretty big deal. There are also a significant number of runtimes and devices that will soon be compliant. This includes SteamVR from Valve, the Vario high-resolution VR headset, and the Monado open-source OpenXR implementation from Collabora. Valve, in particular, have stated that all new functionality for SteamVR will be exposed in OpenXR rather than in their older proprietary OpenVR API. And with version 4.2.5, the Unreal Engine from Epic has enhanced its support for OpenXR, including optimizing reprojection and rendering. And lastly, working group members, including sensor vendors such as Ultraleap and Tobii, have developed OpenXR extensions for hand and eye tracking. And let's just take a look at those in more detail. OpenXR's hand and eye tracking extensions enable developers to build advanced user interfaces. The hand tracking extension defines a hand articulation model that will be consistently exposed by OpenXR implementations, enabling applications to use sophisticated hand interactions that will be portable across vendors' devices. The hand tracking extension is already shipping on the HoloLens 2, and Ultraleap also has a developer preview. The eye tracking extension has been developed by sensor vendors including Tobii and will enable natural eye gaze interactions. And this extension is also already shipping on HoloLens 2. So what functionality does OpenXR provide? OpenXR contains everything an application needs to drive XR devices in a system, including device discovery, event processing, sensor tracking, and post calculations on the input side, and frame display timing and composition, plus haptics control on the output side. However, OpenXR deliberately does not include 3D rendering, and so an OpenXR application will also use a rendering API, such as Vulkan, to generate the imagery. OpenXR can be used with any 3D API, but a new generation API such as Vulkan provides the high performance and low latency that are vital for compelling XR experiences. Whatever 3D API is used, OpenXR provides all of the display parameters necessary for the application to be written to run portably on any OpenXR compliant device. Vulkan and OpenXR are both native APIs. However, the metaverse of openly connected and searchable virtual spaces and interstitial experiences is likely to evolve out of the World Wide Web, and so it's critical that the industry also bring accelerated XR capability to the browser. The World Wide Web Consortium, the W3C, is developing the WebXR standard to bring XR capabilities to the web stack. And the good news is that the Khronos working group is working closely with the WebXR working group to enable WebXR to effectively use OpenXR as a native portability API, saving WebXR from having to be ported to dozens of different proprietary runtime APIs, and enabling XR in the web to be available on any OpenXR compliant devices. And in fact, since version 81, Google Chromium uses OpenXR as its default backend for WebXR, enabling the Google Chrome and Microsoft Edge browsers to already use any OpenXR compatible hardware. As well as providing application portability between different HMD devices, OpenXR can provide portability as AR is deployed on new architectures, such as Cloud XR platforms. Cloud XR can use 5G to enable a lightweight AR device to send its real-time sensor data to an edge server that processes the sensor data and uses powerful GPUs to generate graphical augmentations that are much more sophisticated than can be generated on a battery-powered device, and then are sent back to the device for display. An OpenXR runtime can be implemented to run across both the AR device and the server, with the OpenXR API completely hiding the round trips over 5G from the application. This enables the same AR applications to run natively on an AR device or on an AR device connected to an edge server. OpenXR is gaining wide industry adoption because it's a win-win for all involved. Software developers can write an application once and deploy on multiple hardware platforms without reporting, saving time and money and reaching a much larger market. XR hardware vendors win when they expose the OpenXR APIs on their platform, as they can access a large library of OpenXR compatible applications. And most importantly, end users win, as they know that the applications that they want to run will be compatible with the system that they have purchased, growing customer confidence and growing the XR market for everyone. So finally, let's talk about OpenCL and SPIR-V. OpenCL is the most pervasive cross-vendor open standard for low-level parallel programming. OpenCL is deployed by CPU, GPU, DSP, and VGA, FPGA vendors, and used by an increasing number of applications, engines, and libraries, as well as acting as a backend target for languages, compilers, and machine learning stacks that need a portable API to reach into parallel hardware acceleration. In particular, almost all mobile inferencing engines from companies such as ARM, Qualcomm, Intel, VeriSilicon, Synopsys, TI, and Xiaomi use OpenCL as an acceleration backend. OpenCL is used for cross-platform parallel programming of diverse heterogeneous processors found in supercomputers, servers, PCs, mobile devices, and embedded platforms. OpenCL is a runtime kernel, runtime and programming framework that includes C and C++ based languages for creating compute-intensive kernels that can be compiled and executed across any available parallel processors in a system. OpenCL provides APIs to discover accelerated devices, compile kernels for selected devices, execute the kernels with explicit control over kernel placement, memory allocation, and synchronization, and finally gather back the results. When deciding between OpenCL or GPU APIs such as Vulkan, many developers that don't need graphics rendering find that OpenCL provides a simpler programming model, a lighter weight runtime, more language flexibility compared to graphic shading languages, for example, OpenCL-C has pointers, and more rigorously defined numerical precision for math operations, and that can be critical for many applications. In March of 2020, Khronos released the OpenCL3 provisional specification for industry feedback, and we are expecting spec finalization and first conformant implementations before the end of the year. OpenCL3 enables hardware vendors to focus their resources on the driver functionality that their customers need by making all functionality beyond OpenCL 1.2 optional and queryable through API queries and language macros. This flexibility will enable new extensions that become widely adopted to be incrementally integrated into new OpenCL core specifications. Also, OpenCL 3.0 removed the OpenCL C++ language from the specification and recommends instead the use of the C++ for OpenCL open source front-end compiler that is supported in Clang, leverages LLVM, and generates SPIR-V code. C++ for OpenCL is fully compatible with OpenCL-C and so enables developers to incrementally use most C++ 17 features in OpenCL kernels. OpenCL 3.0 also defines all versions of OpenCL in one unified specification, with the specification source on GitHub for industry feedback and bug fixes. Moving existing OpenCL applications to OpenCL 3.0 is straightforward. OpenCL 1.2 code will need no changes. OpenCL 2.x applications will also need no code changes if the OpenCL 3 driver supports all the functionality that they use. Looking forward, applications that wish to run portably across multiple OpenCL 3 devices should query 2.x level functionality to ensure that it's available on their device. As an example of OpenCL's growing usage in the mobile industry, Google recently announced a port of TensorFlow Lite to OpenCL to complement its existing OpenGL ES backend. The OpenCL port delivers twice the accelerated inferencing performance on the same device and over 4 times the performance of unaccelerated inferencing. Even though not officially exposed as part of the Android platform, OpenCL is often provided by mobile GPU vendors, and it is increasingly being used as an acceleration target for mobile inferencing frameworks, as well as video and imaging libraries. And speaking of inferencing, there's a lot of active research across the industry into enabling machine learning compilers to harness inferencing acceleration, with many companies developing their own machine learning compilation stacks. So for example, Amazon with TVM, Facebook with Glow, and Google with XLA. Now, things may look complex here, but all these compiler stacks follow a similar pattern. Firstly, import a trained network, then apply graph-level optimizations to the network, and then decompose the network into executable instructions. All of these machine learning compilers can emit OpenCL code to portably access parallel hardware acceleration, illustrating again how OpenCL is the most pervasive close-to-metal execution layer for machine learning libraries, engines, and compilers. One particularly interesting open source project from Google is MLIR, which is in active development and includes an ongoing exploration of how to effectively reach down into hardware-accelerated inferencing by using Khronos' SPIR-V intermediate representation. Confusingly perhaps, MLIR does actually not stand for machine learning IR, but stands for multi-level IR, reflecting this key concept of compiling code through multiple layers of optimizations and transformations so it gradually gets lowered towards hardware executable code. The last step of that series of transformations is performed by a related Google open source project called IREE, which performs the lowering into hardware-specific code such as ARM or x86 machine code, or SPIR-V for ingestion into hardware acceleration APIs such as OpenCL or Vulkan. IREE is in research today, but it's certainly an interesting project to watch out for, as Vulkan is Google's primary GPU API. Google's current IREE effort is focused on producing SPIR-V for Vulkan, and when the Vulkan working group is working with Google to experiment on what simple primitives would be the most effective for the IREE compiler to target. In addition, once MLIR and IREE are capable of generating SPIR-V code, then significant deployment flexibility to other APIs such as OpenCL will become possible through leveraging the growing ecosystem of SPIR-V tooling. And SPIR-V, as GPU and parallel acceleration solutions become increasingly dependent on this type of compiler technology, SPIR-V becomes an ever more important part of the Khronos standards ecosystem. SPIR-V is an intermediate language representation that includes constructs for heterogeneous parallel processing and graphics operations that can be broken down into instructions for GPUs and other processors. SPIR-V is the only language directly ingested by Vulkan, and it can be imported into a growing number of OpenCL implementations. SPIR-V enables the hardware and compiler communities to innovate independently. Front-end compilers can simply generate SPIR-V code to be ingested and executed by a wide range of runtime APIs. And as the SPIR-V tools ecosystem grows, developers have significantly more choice over where they deploy their kernel code. For example, it's now possible to compile OpenCL C kernels for execution on Vulkan runtimes. This is a significant benefit to developers that wish to ship portable applications across a fragmented landscape of platforms supporting different runtime APIs. So that's the end of my presentation. As the ARM ecosystem for deploying sophisticated interactive experiences continues to evolve, Khronos remains committed to playing a vital industry role by providing a safe space for companies to cooperate to create open standards that benefit their own business and the wider industry. If your own company would like a voice and a vote in any of these standardization activities, or you wish to implement a Khronos standard on your silicon, Khronos warmly welcomes any company that wishes to participate. We look forward to hearing from you. Thank you.